Good afternoon, and thank you for inviting me. My name is Abhay Joshi, and my collaborators are Shubho Datta and Mike Lang. I modified the title a little bit to reflect the work we have done on two NASA SBIRs. So this work includes work done on both of them. So I'm calling it low noise, large area, high-speed in-gas quad photo receivers and linear arrays for 1 to 2 micron short-wave infrared sensing. Next slide. So just a brief history of the company. We are over 20 years old, a small business, and a majority of our revenues are now commercial, so only 20% come from the government. Some of our customers include NASA, Boeing, Lockheed Martin, Harris, and we are a C Corp. Next. So the first topic, or the part of my talk is going to be on low noise, large area quad photo receivers. This work was funded by NASA Goddard Space Flight Center through a Phase 1 and Phase 2 SBIR. And the program manager was Dr. Jeff Livas. So here we are going to show some of our high sensitivity front-end sensors, which have quadrant geometry for position and direction sensing for long-based interferometry. And Jason Hogan's talk was perfect introduction to gravity wave detection. We think the current TRL level is about 4 to 5. And the uniqueness about this technology is that we feel we have produced the lowest noise, large area quad photo receivers in the world. And we also made attempts to make them red hard by design. So as Jason pointed out, a spacecraft like LISA will have 3 equilateral triangle spacecrafts separated by 5 million kilometers so that you can get decent separation. Like he showed, like 100 kilometers gives 1 femtometer. So to get a decent resolution, you have to have a pretty long baseline. So there are basically free space lights at 1064 nanometer pointing at each satellite. And when we did this work, the wavelength chosen was 1064 nanometer. And that's because these lasers inherently have low intrinsic rim noise. And we were told to make detectors for 2 megahertz to 20 megahertz IF range. And each quadrant had to handle more than 100 microwatts because it's a optical LO-based system, a coherent system. And the equivalent input noise had to be less than 4.7 picoamps per square root hertz. So this is the detector which we did for Goddard. It is a quad photo detector with A, B, C, D quads. The diameter of that quad is 1 millimeter. And we had to get low noise. So from the geometry, you wanted as large area as possible with least capacitance, which gives you low noise. And we also needed small crosstalk for better position and direction sensing sensitivity. And the devices had to be red hard by design. So this is the deliverable we gave to Goddard. So this is a packaged quad photo receiver on a driver board. And so this device is inside with a TIA. So this is the cross section of the device. It has 2 microns of in-gas, which is the absorber, which absorbs 1064 nanometer light. Then we put an 8 micron buffer made out of indium phosphide. So this does not absorb photons, but we deplete it, and that's why we call it dual depletion, to achieve low capacitance. So by depleting this whole 9.5 micron region, we can get the least capacitance, which gives you low noise. So we got a patent for this, and that's the patent number. And with a 2 micron thick in-gas absorber, we get about 0.7 amps per watt responsivity at 1064 nanometer wavelength. So here is some data. So this is the capacitance of the quad. So this is the capacitance of the individual quad. So at about full depletion, about say 10 volts, you get about 2.25 picofarad capacitance. So this is by far the lowest capacitance of such a large area quad. We also measure the dark current. The dark current is about 150 nanoamps. But because this has a local oscillator power of 100 microwatts, which will produce 70 microamps of photocurrent, the dark current noise or the short noise coming from dark current is negligible. So these are the different noise sources coming from this device. So this is what we delivered to Goddard. So this is the photodiode and its equivalent circuit followed by the op-amp. Goddard chose this intercell op-amp whose noise current density is 0.9 picoamps per square root hertz. The VNA is 1.5 nanowatts. And so when we do all these calculations, these are the different noise sources. But here is the LO short noise for a 100 microwatt local oscillator. So basically this is a short noise limited link if you choose a decent LO. This is another picture of the device we delivered. So this is a TO3 can. We use a 1 millimeter thick aluminum cap and a sapphire window with an anti-reflection coating at 1064 nanometer because that was the wavelength chosen by Goddard. And essentially this thick aluminum coating prevents the electronics like the op-amps, the intercell op-amps from being exposed to direct radiation. So hopefully that will make it more dread hard. So this is the RF response and the noise results. So from each quad, we get about 20 megahertz 3 dB bandwidth. The conversion gain at 1 megahertz is pretty high, like 41 kilowatts per watt. And the noise which we achieved at 1 megahertz and 20 megahertz was way below the spec of what they wanted us to do, which was 4.7 picoamps per square root hertz. So we got about 1.4 to 1.7 picoamps per square root hertz from this whole 1 megahertz to 20 megahertz IF range. And so we met all the goals which Goddard wanted us to do. So what's the current development status of this technology? So commercial products are available, what I just showed you for benchtop lab use. Of course, if you want to launch this in space, we need to do radiation testing. And we anticipate if this device were to be fully red hard qualified, it will take about 3 million USD. It's because the number of tests you have to do, the number of sample size you need. And why would NASA or other agencies invest in this technology? Well, the low noise, high sensitive optical front end detectors are vital for free space sensing and communication links beyond the LISA application. Next. What are the target technology market? Essentially for NASA, it's the long baseline laser interferometry, wind profiling, planetary mapping. Military has, of course, some of its usage. But in commercial arena, there are plenty of uses like wind monitoring at airports, biomedical imaging, and spectroscopy, among others. Next slide. Okay, so that was part one of my talk. The second SBIR, which we worked in last few years, was also funded by NASA Goddard. We did phase 1 and phase 2. And this was to develop essentially fast linear arrays and 2D image sensors. So the work I'm going to show is for that SBIR. The current TRL level is 4 for this. And so what's unique about this technology, we are trying to do a fast optical detector for 1 to 2 micron wavelength, which will allow for an uncooled operation and again, hopefully red hard by design. So this is the different elements which can be detected between UV to shortwave infrared up to say 2500 nanometers. So most of the key elements for essentially greenhouse gas detection fall in this range. And so image sensors going from UV to SWIR are of great interest to NASA. So what we are trying to do here is try to get a very fast photodetector, which will allow for a shorter integration time in conjunction with high-speed readout integrated circuits and achieve higher SNR. Just to show a little bit of material science here, this is the indium phosphide substrate on which we grow all these epitaxial layers to achieve the desired wavelength up to 2 micron in the infrared. So the key thing mainly is the lattice constant of the substrate is 5.86, whereas the composition of InGas required to go beyond 2 micron makes the lattice constant 5.94. So there is a difference in the lattice constant of the epitaxial layers and the substrates, which creates so-called crystal misfit dislocations. So the challenge is to keep those misfit dislocations small enough and get still full bandwidth. So these are the pictures of a 16-element linear array with a 200 by 200 micron photodiode array, and this is with a 32-element 100 by 200 micron. These geometries were again given to us by Goddard. And so this is essentially the dark current and the capacitance when we deplete it up to almost 10 volts. And the capacitance basically of these devices is pretty low, that one could get bandwidth in the vicinity of 1 gigahertz. So if you get a fast readout integrated circuits, you can have a pretty low integration time and be able to use these arrays. We also did two-dimensional image sensors for Goddard. This is a picture of 4 of these 512 by 640. And so this was processed to be compatible with FLIR's 9803 ROIC. The spacing between each pixel is about 25 microns, and the actual PN junction is 6 micron. And so this is the dark current and the capacitance of such a small pixel. To show the speed of what we can achieve with these detectors, this is something we did in our lab. This is the 3 dB bandwidth of a 30, 40, or 50 micron photodetector made out of 2 micron material. And you can see they can go beyond 20 gigahertz. And this is basically packaged in a fiber optic receptacle package, so we can test it with a telecommunication grade equipment. And so this is a 10 gigabit eye diagram of our 40 micron diameter PD along with a Pinty eye, and you can see the eye is very clean. So we showed here that these devices can be used up to 10 gigabits. Okay, so what's the current development status of the technology? Again, these are available for benchtop use. Same thing like the previous one, radiation testing needs to be done for space qualification. This one will require, we believe, more money because more is involved. So we think it will take up to $5 million to get it space qualified. And again, why it's important, should be important to NASA, is basically improved speed of optical detectors, again, in conjunction with high-speed ROICs, will allow for operation of the sensors at a relatively warmer temperature from 250 to 300 Kelvin. So the target technology market applications basically is weather observations, sensors for planetary missions. This is for NASA. Military has quite a few usages here for commercial applications. It could be used for biomedical imaging, crop monitoring, mineral detection, among few. Next slide. So that's my name. That's me from Discovery Semi. One more. Next. And just a key point, so we have an established track record for building high-quality photodetectors for aerospace applications, and we have a 4,000 square feet Class 100 clean room near Princeton, New Jersey. And the part of our SBRs, these are the deliverables we made to the government. For the quads, we delivered 2 1mm diameter quad photoreceivers in a TO package, and 4 1mm package with the driver boards. And for the 1 to 2 micron photodiode array project, we delivered 4 512 by 640 2D arrays, and 2 200 by 200 linear arrays, and 2 200 by 100 micron 30 mm linear arrays. Thank you.